Hold on to your pantaloons. Got lots of examples to try and cover to give you as many situations covered as possible. We're continuing with finding logs. We're just making them uglier and uglier. Whenever you're being asked to find a log of an expression, right? So there's more than one piece inside the log. It's a very good idea that you use the law of logs over here, which I've rewritten because I couldn't find my old ones, to break this apart into smaller pieces. And you try and break it into the smallest possible pieces that you can. So here goes. I'm thinking this is 1, 2, 3 pieces. These two are multiplied, so that's the log of t plus the log of t squared plus 1 to the 6. And this is on the bottom, so it's essentially dividing. And dividing gives you take away the natural log of, in this case, the 9th root of tt, 2t take away 1. So that's your first job. Break it apart. So things that are on the top are multiplied, you add them. Things that are on the bottom, you subtract the log. And that's basically rows 1 and 2. And sometimes you can do a little bit more. Sometimes you can use rule 3, which basically takes powers and square roots and makes them into multiples of a log. So this is the log of t, this is good. This guy to the power of 6 can be written as 6 times that fella. And square roots, cube roots, and in this case, 9th roots give you fractions. So a 9th root gets you a 1/9 power. And so you get that. So basically you take the original ugly log and break it into lots of baby logs. And now you can do the differentiation, one piece at a time. The derivative of that is 1 over t. This is going to be a chain rule, and that's going to be my inside function. So it's going to be 6 times 1 over t squared plus 1 times the derivative of the inside function, which is 2t. This one is going to be 1/9, 1 over 2t take away 1 times, and this is an inside function, times 2. And then all you need to do is essentially tidy up things as best you can. And you're finished. There's very often not a lot of style points that you're going to have to deal with these kinds of questions. They're just too ugly. Right? There's not a lot you can do with them. And even if you try to make them into a single fraction, that single fraction would probably be even uglier looking than this, so there's no great deal points there. So be comfortable about the process. Take the log of the expression and break it into separate pieces. Tidy them up if you need to. Differentiate, and then make it look as pretty as you can. Can anybody see anything you can do to the inside that might be worth it? Anything algebraically you can do to e to the negative x plus x e to the negative x?
Like vector?
Didn't catch that? What did you say?
Like vector it?
Yeah. And e to the negative x would be a good factor, right? Now let's see why that might be helpful. Well, in this format, you cannot call this the log of that plus the log of that. Log rules only work for things multiplied or divide or square roots and powers. So pulling this out as a common factor, that allows me to separate it. Two things multiplied become 2 logs added. It's a little bit nicer. This is a power. It's like number 3. So any power can come outside, negative x, log of e, plus that guy. Now we're almost finished. The natural log of E is a number, but it's quite a nice number. What number is it?
1.
So this is negative x times 1, which means it's just negative x. So that was the original log, which would have taken a fair amount of time if we had left it that way and just went straight into the chain rule. Instead, we've rearranged it algebraically to be this expression, which is the equivalent of it, but much nicer to differentiate. Because that guy is negative 1, and that guy is 1 plus x. Look good? So algebra can be your friend. Okay, one last example of this type. This is a natural log of the square root of an ugly fraction. Anybody tell me how I could rewrite the square root as a different log? How could I take a square root and rewrite it so that it would look nicer?
Rewrite them as to the 1/2 hour.
And pull it outside. Correct. So square roots get you half powers. If this had said cube root, wouldn't I just put a third here? If it said a 9th root, I'd put 1/9 there, right? Now that's a little bit nicer, a little bit easier to differentiate, but we can do better. How could I rewrite the log of this division in terms of 2 separate logs?
The natural log of A minus natural log of B.
So top one, correct. Take away the bottom one. Right. And I would, at this point, to make differentiation a little bit easier, is I would separate these out. Like that. Okay, so started life off as this. Now it's being returned or replaced by this. Now we differentiate. Actually, the differentiation is very often the easiest piece of the puzzle. Now this is going to be a chain rule, and that guy there is the inside function. So you get 1/2. To differentiate a log, it's 1 over the thing, inside function, times the derivative of the inside function. Take away 1/2. The derivative of this log is 1 over the inside function times the derivative of the inside function. And that 8 and that 1/2 get me 4. And that negative 8 and that negative 1/2 get me plus 4. And we're finished. So even the ugliest looking log function with a little bit of work can be turned into something that's relatively simple. Any questions about the last 3 that you're not sure about? Okay. Now there are tons and tons of variations, so you just have to kind of know the process and then adapt it to the situation. Next group of questions, I think there are only a couple of these are some examples of them, where you've been asked to find the first and the second derivative, right? So basically you've been asked to find y dashed, y double dashed. And here are 2 examples. Here's my first one. There really isn't any algebra to do. That's the way it's going to stay. But do you see a product rule? Right, it's an x squared times a logs. X a product rule. So its derivative is going to be f dash g plus f of g dashed. It's going to be 1 times the natural log of x plus x squared times the derivative, which is 1 over x. And then tidy it up a little bit. I get log x plus x. That's probably a lot nicer than you thought it was going to be. Now you differentiate it again. That guy's going to be 1 over x, and that guy's going to be 1. Are we good? So that would be an example of a first and second derivative question, which went pretty smoothly. So let's have a look at one where things kind of go wonky. There is no algebra that you can do to make this pretty. So try to know when you can do things and when you can't. Whenever you see two things added inside the log, it's dead, right? There's nothing you can do to it. This question is actually going to be a chain rule. I'm not going to touch it in any way, change it in any way. It's a chain rule. This guy here is the inside function. So derivative 1 over the inside function times the derivative of the inside function, which is 1 over x. So we now have that guy. Not anywhere near as pretty as we would, that this one was, right? Pretty messy, actually. Product rule, quotient rule, chain rule. What will I use to differentiate this function to get the second derivative? Product rule, quotient rule, or a chain rule?
Product rule, right?
Well, you see a product on the bottom?
Could you do that?
Well, unfortunately, because there's a 1 on the top, it kind of stops us doing that directly. Although you're half right there, because there will be later on a product rule. But right now, it's a quotient rule. And the reason it's a quotient rule, because it's a fraction. Now, when you get a difficult fraction to do, I set it up at the side. Top's the easy one, because the derivative of 1 is 0. This is the quotient rule you were thinking about, and you're right, there is one. Isn't the bottom function, the g, 2 things multiplied? So to differentiate that guy, I will have to do a little baby product rule. We'll have to call this fella f and this whole piece here g. So it's going to be 1 times the natural log of 7 plus log x added to x times, and the derivative of that is 1 over 7 plus n L of x. God, that's ugly. I'm going to have to move this over here. So it's going to be f dash g, take away f of g dashed, all over g squared. Right. F dashed is nothing, so I don't really care what g is, because it's going to get multiplied by 0 and disappear anyway. Take away 1 times g dashed, which is quite a lot actually. It's the natural log of 7 plus the natural log of x added to x over 7 plus the natural log of x. And the whole thing is over this guy squared, which is x squared, 7 plus the natural log of x squared. So one example, which is very nice and very simple, and one example, extremely ugly. Now, I've got 0 and negatives, that basically gives me that guy. And so I'm going to have negative, I'll make the whole thing negative, that's probably at least amount of work. And that's probably one of the ugliest looking answers I've ever seen. I'm not even sure I could do anything to it that would be worthwhile. Style points. I guess I could multiply the top by this and this, but that wouldn't do much good, to be honest. So I'll leave it. And that one was not fun. Any questions? That one you may want to look at slower on your own time. Okay, let's do a pretty, right from horrible, let's do something pretty straightforward again. So there are some questions where they ask you to find the equation of a tangent line. The one that I'm choosing just to show you the process is this log function. And we're being asked to find the equation of the tangent line at a given point. Finding the equation of tangent lines is a pretty common thing to be asked, isn't it? You know, you get that pretty much every section. So here's the job. Step one, find the derivative. Well, in this case, it's 1 over x squared take away 8x plus 1, since it's a general, times the derivative of this fella, the inside function, which is that. So the derivative, if you can make it look a little bit prettier, looks like that. Then you find the derivative at x equals 8. That's 2 lots of 8 take away 4 of 8 squared take away 8 times 8 plus 1. That's 4. 2 4s get you 8. That's 64. That's take away 64. So you get 1. And so we now know the slope of the tangent line is 8. Can anybody tell me the point slope equation, which is the last part? The point slope equation of a line.
Y minus y1 equals x bracket. Oh wait, no, slope, and then brackets x minus x1.
Yes. And that's x1 and that's y1. So it's going to be y take away 0 is 8, x take away 8, and that's going to get you your answer. Now, if we had time, wouldn't I plug that into Desmos? And wouldn't I plug that into Desmos? And wouldn't this straight line touch the curve at 8, 0, like a tangent line, right? And that would be a way to check it. So equations of tangent lines are pretty straightforward. Find the derivative, evaluate it at the x coordinate, that'll give you the slope of the line, and use the point slope equation, and you're done. Any questions about equations of tangent lines? Pretty straightforward, as long as this isn't too ugly. Well, I told you at the beginning today we had a lot to do. There are 2 topics left. One is finding the derivative of inverse trig functions, which is basically just the chain rule and memorizing some answers. And then we have logarithmic differentiation. And logarithmic, I can't even say the word today, logarithmic differentiation is scarily ugly. But once you've figured out how to do it, it's actually not bad. So what do you mean it's scarily ugly? The first couple of times I do this, you're going to go, what the heck's it doing and what's next and why? But if you see enough of them, you'll start saying, oh, it's just a trick. a way of getting round finding derivatives of really ugly or weird functions. So logarithmic differentiation is a niche market. It's used for finding weird powers. That's one of its biggest jobs. That, in my book, is a weird power. Right, x cubed is normal, right? X to the -2, even x to the half is okay, right? Because those are just power rules. This is not, let me say that again, not a power rule. So if you think, oh yeah, you just go sine x times x to the power of sine x minus 1, right? Just doing the power rule. It might seem that that would be a sensible approach, and I'm sure it is a sensible approach. It's also wrong. It's not the answer. The way you get the derivative of weird powers, like this one, involves a technique called logarithmic differentiation. So here goes. The first step in this process is one that you wouldn't think to even do. So the guys who figured this out, the girls, whoever it was, they were being really sharp. The first thing you do is take the natural log of both sides. Now, would you agree that's kind of weird? Why would you even want to do that? Because it doesn't seem to bring any benefit. Would you agree it makes the thing worse looking than the original? But nonetheless, it helps. Now, the third law of logs says that the log of a to the power of something, right? Where a is whatever you like and n is whatever you like. So this is the a and sine x is like my n, can be written as sine x times the natural log of x. And that's step 2, because that pretty much always happens. You still with me? So I've took the log of both sides, and then I've used the third law of logs to get rid of the power, to write it like this. Now the third step is that we differentiate. Now forget about this for a minute. If I asked you to differentiate sine x times log x, would you all agree it's a product rule? Right. Sine x times log x, if I said differentiate that, I'm hoping that you would say it's a product rule, which it is. And that is the derivative of a sine is a cosine. And then you leave the second function alone. Plus you leave the first function alone and you differentiate the g. So far, so good. Differentiate. All I'm doing here is tidying things up. I'm not even sure it's probably worth it, but I'm doing it anyway. Yeah. Sine x times 1 over x is bad news, right? It looks a little bit better that way. Now, I said we're going to differentiate this side, which we've just done. I also am going to differentiate this side. So this is weird again. I'm going to differentiate the natural log of y, and I'm going to use implicit differentiation. Now, if you differentiate the natural log of y, don't you get 1 over y times what?
dy dx.
And that 1 over y dy by dx is always going to be there, because it's always going to, the first 3 lines are always going to look like that. So this will be common in every question. This depends on what you've got, but this is common. Now, the goal here is to find the derivative, which means we are trying to find out what dy by dx is. Okay, what should I do to both sides to isolate dy by dx?
Times it 1.
Is it? This is it. Last line coming up. In questions like these, you don't want your answer in implicit form. Do you know it's okay when you do implicit to have X's and Y's jumped up? In fact, that's what you tend to get. We want everything in terms of X. So I need to figure a way of turning that guy into X's. So the final answer is going to be cosine X log X plus sine X over X times what? What do I replace the Y with that uses X's? And it's on this piece of paper.
dy by dx.
X to the power of sine X.
Yeah, you see it up there? Right. I tried to take that as slowly as I can. Would you agree this is a very weird way of finding a derivative, right? But once you, hopefully this is only the first time, but are you beginning to see there's a kind of logic to it in the way that you do get the answer once you're finished? Okay, let's do another one. No, I didn't. That one, the one I just did, looks like that one. That's not different enough to make it worthwhile. Yeah, why don't we do 22? Whoa. The sine of 3x all raised to the power of log x. That is one weird looking function. So first thing I'm going to do is take the natural log of both sides. So that would be step one. How will I rewrite this ugly expression?
Well, that's
Log,
the ln of x times ln of sine 3x.
you all comfortable with that? Okay. Power comes downstairs. Now we're going to differentiate. This is going to be fixed. This is kind of what you always get on the left. On the right hand side, pretty much same situation. You typically get a product rule. And that guy gets me 1 over x, and you leave this one alone, plus you leave this one alone. And now you have to be a little bit careful. I'm now going to differentiate the natural log of sine of 3x, which is 1 over the cosine of 3x. But isn't it a chain rule, right? So it's not just 1 over, oh yeah. I'm thinking ahead here, sorry. It's 1 over the sine of 3x. It's not just 1 over the sine of 3x. Don't you then have to multiply by the inside function, which is where that cosine that I put in the wrong place was coming from. So if you differentiate 1 over the sine of 3x, sorry, the log of sine 3x, you get 1 over the sine of 3x times the derivative of the sine of 3x, which isn't just the cosine of 3x. Isn't it a chain rule inside a chain rule? So if you differentiate the sine of 3x, you get the cosine of 3x times what? Derivative of sine 3x is cosine of 3x times something. I didn't catch that.
3.
Agreed. So I'm just tidying this up a little bit. Got this guy. Not at all pretty, agreed. But it is what it is. So what do I do to both sides to get dy by dx? So I'm going from here to here. What do I do to both sides? I multiply it by y, don't I? And then I notice something, which I'm now going to fix. The cosine of 3x on the top with a sine of 3x on the bottom becomes what? What's a cosine over a sine? Trig identity. Cosine on the top, sine on the bottom. What do you get? Any takers? Cosine over sine. It's okay to be wrong.
Cotangent?
It was, yes. So it's 3 cotangents of 3x, 11x. And we multiply both sides by y to get here, and that y gets replaced by the original. And when you look at how ugly that answer is, I really think if you didn't have this method, I don't think you could have guessed that the derivative of this is that. Would you agree? It's just too out there to be even guessable. And that is the end of logarithmic differentiation. Any questions before we move on to our last piece of the puzzle?
Can you just put the last paper on this side?
Sure. Once I find out where I put it. There it is. Any questions before we move on to our last topic then? Well, here it is. Making no attempt to prove these to you, but we could, and you can go and look online for it, you can prove it using implicit differentiation. Now, the derivative of these 3 inverse trig functions, inverse sine, inverse cosine, and inverse tangent. Remember those functions from 142, the inverse trig functions? Sine, cosine, tangent. Technically there are 6, but in practice these are the only 3 you need to worry about, right? Inverse sine, inverse cosine, inverse tan. You'll also find them, not so common now, but some textbooks do use them, arc sine, arc cosine, and arc tangent. These are just different names for the same thing. Now, the derivative of the inverse sine function is 1 over the square root of 1 minus x squared. The derivative of the inverse cosine is just minus 1 over that guy. And the derivative of the inverse tan function is 1 over 1 plus x squared. So you just memorize those guys and you're good to go. So we are just going to look at finding derivatives of functions that contain one of those three inverse trig functions. First one, a version of 23. And before I continue, this is inverse sine function. It does not mean, sine to the power of -1, right? It might look like, I know it does look like it, like this is a -1 power, because see, if you put a little 2 here, doesn't that mean sine squared, right? But this is just a notation. When I take over the world, it's not going to be called -1 anymore. It's going to be called sine star of 4x, right? I'll have a new symbol. But since I haven't taken over the world yet, we'll have to use these ones. This is a chain rule. It's the inverse sine of 4x. Now the rule here is that its derivative is 1 over the square root of 1 minus x squared. But I don't want you to get too caught up on the fact that this is x squared. I want you to think of this as a placeholder. So whatever here goes there. So if this is 10, this is 10. If this is 1,000,000x, this is 1,000,000x. In this case, it's 4x. So it's a chain rule. Now the inverse sine of 4x then is 1 over the square root of 1 take away 4x squared. You see what I'm saying here? That x is really just a placeholder for whatever is here. So if you have a 4x, you put a 4x in. Now I did say it's a chain rule as well, because after you've found the inverse sine part, don't you then have to differentiate by the derivative of the inside function? And what is the derivative of 4x? Okay. Now, to make it look pretty, and there's not actually an awful lot you can do to make it look pretty. You do that, and you're finished. So compared to logarithmic differentiation, would you agree these are a lot cleaner, a lot less to worry about, at least in this question? Let's try 24 then. A little bit harder this time. We're going to do an inverse term of the square root of x minus 9. Now this guy here, this whole square root thing, is my inside function. This whole square root thing is that guy. So when you differentiate, you are going to get 1 over 1 plus the inside function squared. Are you comfortable about the derivative of an inverse tan is 1 over 1 plus the thing inside squared? Then you do the derivative of the inside function. And I'm going to just call it what it is. You then multiply by the derivative of the square root of x minus 9. And then somewhere at the side here, let's find the derivative of that guy, right? Is there another way I could write this so I can find its derivative?
Put it to the half power.
Agreed. And then its derivative, which is what I want to go here, is going to be multiplied by the power and reduce the power by 1. Technically times the derivative of the inside function, but since that's 1, we don't really do anything about it. Make it look pretty. Negative powers go downstairs. Make it look like the original. And there's our answer. So it's 1 over, okay, what will happen to the square root of x minus 9 if you square it?
It'll just become x minus 9.
And this weird derivative that we just found? Okay. Is there anything left to do? Well, let's phrase it a different way. What is there left to do to make this prettier?
Add like terms in the bottom of that one.
So basically you're going to get an x minus 8, aren't you? And if I'd thought about it, I would have done this a little bit better, but now I'm ready. There's your answer. Are we good? Inverse tan. Right. We don't have too much time, so let's see if I can do a chain rule now. With we'll use their notation. So this is a version of 25. So we have a function that is an arc cos of x multiplied by the natural log of x. That is my f, this is my g. So I'm doing product rule. Right. Arc cos, right, is the same thing as the inverse cosine. So its derivative is -1 over the square root of 1 minus this guy, right? So its derivative is -1 over the square root of 1 minus x squared times g plus the arc cosine of x times the derivative of 1 over x. And you know, and sometimes you just have to do this. There is nothing I can think of that would make that any prettier. So we're finished. You know, sometimes you just get a function that you can't do anything to it. So our last function for today is going to be this one. We've got that guy. Take away that guy. Well, there is an awful lot happening in this question. There's really two different things happening. I'm going to take this guy and differentiate him. And then I'm going to take that guy and differentiate him. And then this answer, take away that answer. So really I've got a lot of different bits, a lot of moving parts here. So let's focus on just differentiating this piece. Just like in the previous question, you call it a half power. We can use a chain rule. So it's 1/2, 1 minus x squared, reduce the power by a half, times the derivative of the inside function, which is -2x. That guy and that guy gives you that. That guy comes downstairs. And then you make it look pretty by returning it back to its original form. So that guy is hidden. So we've done one piece of the puzzle. Then why did that turn into a plus? Who knows? It's a minus. Now the second one is an x inverse cosine of x. And if I want to differentiate that guy, it's going to be a product rule. Differentiate this guy, you get 1, leave that guy alone. plus leave this guy alone and differentiate that guy, you get -1 with that guy. Really not an awful lot I can do to make that look nice. So it's going to be take away that guy minus that guy. And so we have this ugly fraction. Take away that fella. Take away a negative. Add this fella. Oh, isn't that pretty? What do you notice happened here? Can you see anything nice happening here?
Those two cancel out.
And so what you're left with when you looked at the original function, which is this, would you have taken bets that its derivative would be so pretty? That is quite amazing. Kind of nice. Well, we are finished with that one section. This week is going to have one section of homework, basically on the topics we've covered, and due on Sunday midnight, and an online test 6, which would contain nothing but these questions. So you only have one focus, well, two. You have logarithmic and inverse trig, right? That's your two things you're going to be dealing with. Hopefully you'll get a nicer weekend because of that. No class tomorrow. I'll be at meetings and things, but you won't be around. So there won't be any officer because I'll be at a meeting, and so I won't be around. So last name, bye-bye.
Thank you. Bye.
Bye.
Thank you.
You're welcome. Edward, do you have a question for me? Otherwise, I'm going to be leaving. Okay, I am leaving.